Not all imbalances are bad, but obviously there are some that are potentially disastrous. If this truck keeps moving without serious correction, it will tip over. A lot of systems are inadvertently put into production with imbalances. While an imbalance will probably not tip the system over, it's important to know if they exist, as they can limit the system throughput. In this case, I'm going to show you how easily it is to identify and correct front-end imbalances within a 3-par system. In the next screen, I'm going to show you how well balanced 3-par's front-end ports are. This chart has 1 bar for each system, representing the fiber throughput in megabytes per second. In the case you can see that the bar on the left is bigger. This indicates that the system monotis _2849_0 has a greater amount of variance. Let's drill down on the system and just see how well the workload is distributed across the ports. In this balance chart, we see that the top 4 ports have significantly higher workload than the rest of the ports, with an average around 60 megabytes per second and peaks up to 185 megabytes per second. Let's take a look at the speed of the ports on these busy ports. The port speed is rated at 8 gigabits per second. The current peak is around 185 megabytes per second, or 1.85 gigabits per second. So the port is currently operating at about 25% its bandwidth. Depending on the mix of reads and writes, the transfer sizes, and the efficiency of the processors, the port may not be able to reach close to its maximum. Typically, ports are able to achieve about 75 to 80% of their rated throughput capacity before a bottleneck is hit. In this case, we're not overly concerned with the imbalance, because even though the peak workloads are at 185 megs a second, there's still plenty of headroom on these ports. In any case, it's a good idea to understand the process for rebalancing the workload across the existing ports. So we're going to take a look at what we might do in order to rebalance the workload on these busier ports by drilling down from one of the ports to the associated volumes to understand which hosts and volumes are on those ports. This chart shows the volume throughput for the top 30 volumes associated with these busy ports. In this case, there are peaks at 10 a.m., 2 p.m., and 4 p.m. Let's take a look at which host is driving the load. The associated host system is named UGKAA796. Let's take a look at how much work is being driven by that host. You can see that almost all of the workload on these ports is associated with this one host. So the only way to reduce the amount of throughput for these ports is to spread the host I/O across additional ports. But this would require additional host ports as well, so it's not really a practical fix. So these ports should continue to be monitored to ensure they are not reaching their throughput limits, so that you would avoid response time issues. If you had a host with a lower amount of I/O that you wanted to move, which would distribute the workload more evenly, that would be feasible. In conclusion, you can utilize balance charts to see any kind of imbalance. In this case, we looked at front-end imbalance. The goal would be to determine if the ports are saturated. If they were close or nearing the performance limit, then you'd want to see which volumes or systems are associated with those ports and migrate or rezone the host to different storage ports. In this case, it didn't make any sense because the port throughput was so low.